Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we are expanding the DSTG Bayesian framework in the search for MH370 to include multiple solutions. In previous episodes, we have looked at the DSTG model in detail and proposed relaxing just one assumption, that there were no active pilot inputs after the Andaman Sea. One or more additional autopilot-directed turns during the following 5 hours and 42 minutes from over the Andaman Sea to the southern Indian Ocean remains conceivable, especially if an active pilot was present. The Boeing 777 guidance mode allowed both waypoint diversion or recommanded heading or track changes. The DSTG analysis provided a rigorous Bayesian estimate of the most probable crash location based on the information available at the time. Although the route dynamics are relaxed, the measurement model is unchanged. Consequently, all candidate trajectories must remain consistent with the full sequence of Inmarsat BTO and BFO constraints, including the 7 arc positions at their respective handshake times. The absence of wreckage after exhaustive underwater searches provides new information that can be incorporated into the same Bayesian framework. Updating the model with these additional observations allows the posterior probability distribution for the final location of MH370 to be refined. MH370 disappeared into one of the most remote regions on Earth. For over a decade, we have been asking a simple question: where is the aircraft? But perhaps that is the wrong question. Today, we approach this differently. The real question is, what does the evidence actually tell us when analyzed correctly? Today, we bring together two analytical frameworks: a Bayesian probability model developed to guide the search, and a global radio signal network that may contain traces of the aircraft's final flight. And we look and see what happens if we combine these two models. This analysis does not attempt to prove a new solution. The DSTG Bayesian model does not produce a single path. It produces a probability distribution. It combines satellite data, aircraft performance, and statistical priors. The result is a map of likelihood, not certainty. The purpose of my present work is therefore to update the Bayesian model to incorporate both the search results and the expanded trajectory hypotheses. Both models begin from the same known point, the penultimate radar detection at 1801 UTC. This shared prior anchors both frameworks. From this point forward, all trajectories are constrained. Both models must satisfy the same satellite measurements, the Inmarsat BTO, burst timing offset, and BFO, the burst frequency offset. And these constraints define distance and motion, but not a unique trajectory. Initially, the models converge. Both frameworks broadly align during the early southbound phase. This agreement is driven by strong satellite constraints. A second dataset begins to show structure. WHISPER detects signal anomalies across a global radio network. In total, we examined 75,822 WHISPER links globally, and that resulted in 125 anomalous WHISPER links. And when filtered, patterns begin to emerge. From these 125 anomalous WHISPER links, 16 of the strongest anomalies were selected for analysis. A divergence emerges later in the flight, around 14 degrees south. So we test the model. If we allow 2 additional turns toward valid operational waypoints, the feasible trajectory set expands. These are not arbitrary deviations. The turns are structured, consistent with standard flight operations, and geometrically coherent. Every trajectory must pass the same tests. All candidates must satisfy BTO consistency, BFO consistency, aircraft performance constraints, and no path is accepted without meeting all three. Within this expanded space, something important appears. The WHISPER-derived trajectory can be shown to fit within the valid solution set. It is not an outlier. It is a feasible member of the solution set. But feasibility is not proof. The WHISPER path is not unique. It is one of multiple trajectories consistent with the evidence. There are limits to this approach. WHISPER remains experimental. Signal interpretation carries uncertainty. Multiple solutions may still exist. So what does this actually give us? This analysis does not locate MH370. It expands what remains possible, and that distinction matters. Bayesian analysis does not provide a single answer. It defines the boundaries of possibility. Therefore, one or more additional autopilot-directed turns during the 5-hour, 42-minute flight over the southern Indian Ocean remain conceivable. This framework evaluates competing hypotheses. Oliver Plunkett, the CEO of Ocean Infinity, said recently that if nothing else, we can say with confidence that MH370 isn't where we looked. That matters. It brings clarity, and it will help those continuing to study the evidence refine their thinking and shape future search strategies. So how should we refine our thinking and shape future search strategies? Approximately 260,000 kilometers of seabed have been surveyed, with high confidence detection probabilities exceeding 90% across most of the search region. Ocean Infinity has spent around $40 million at its own risk. Today, we make a proposal as to where we should look next. The WHISPER model meets the same criteria as the DSTG model. The Inmarsat satellite data at each of the 7 ARC, both BTO and BFO data, are met. The WHISPER crash location is centered on 29.128 degrees south, 99.934 degrees east, and within a circle with a radius of 30 kilometers. Data recovered from Captain Sahari Shah's home flight simulator indicates a flight path that intersects the 7th arc at approximately 29.1748 degrees south, 98.9251 degrees east. The Whisper area has not yet been searched. Independent aircraft investigations brings you the established facts and in-depth analysis. Daily airline news brings you aviation news as it happens. Any interpretations shown in this episode remain subject to revision. Thank you very much for watching.